So thank you very much, and I'd like to thank the organizers for their invitation and for their very warm hospitality. And should also want to mention about Professor Ramurthy that even though I didn't have much opportunity to discuss mathematics with him, when I finished my PhD, I think some words of inspiration from him were all that I had to move on. So with that I will start. And so my talk will be on Siegel modular forms. So as the title shows, so I will try to characterize Siegel cusp forms by the growth of their Fourier coefficients. So So first I would like to recall the basic notions of Siegel modular forms. Just to say notation, Professor Conan has already defined them, but nevertheless let me start by quickly recalling some basic facts about Siegel modular forms, which are nothing but a natural generalization of elliptic modular forms, which we have come across several times in this conference. So the Siegel upper of space is a set of all n by n symmetric matrices over the complex numbers, which have positive definite imaginary part. And the Siegel modular group, or the symplectic group of order n, is sometimes we denote it by gamma n. A set of all matrices, 2n by 2n matrices, such that n transpose Jm is J. It's automorphism group of the quadratic form defined by J, and over the integers. And we will be considering subgroups of these symplectic groups. And first let us see, just recall the action of Siegel modular group on the generalized upper of plane. Like the usual degree 1 action, it's just the, now you just have matrices, that's all. And you also have an action of gamma n on functions, and so for that you fix an integer, non-negative integer, and this is the action. It that cz plus d to power minus k times f of gamma z. So it's really an action. And let's now quickly recall the Siegel modular forms. The space of Siegel modular forms of weight k and degree n for some congruent subgroup. This I presume they are, I don't recall the definition, but there are certain subgroups which are holomorphic functions from Hn to the complex numbers, which are invariant on the action of gamma. And when n equals to 1, we require some growth conditions, the cusp. For n, we do not need this for n bigger than 2. So this, the space of such functions is a vector space, and they also have a Fourier expansion, and that's the main topic of this talk. So since they are invariant under some group of translations, they do have a Fourier expansion, where I just wanted to set up some notation. The Fourier, the indexing set is now the set lambda n or lambda n plus is the set of all n by n symmetric positive semi-definite half integral matrices over Z, and half integral matrices are those for which you have the diagonal elements are integers and the off diagonal elements are half integers. And we just say that the Fourier expansion is supported on lambda n, or supported on lambda n plus, or whatever set, subset you want to say. And this Fourier expansion is also true at the other cusps, which just going to define. And so these are the cusps. The zero-dimensional cusps is this double coset space. It's an union of finitely many double cosets, and by abuse of some notation, we just call this omega j. It should be j, omega j as the cusps. So it should be really the double coset, but there are finitely many cusps. And where the gamma is your the congruent subgroup, gamma n is your Siegel modular group, gamma infinity is the gamma intersection of the Siegel parabolic subgroup. The thing which defined by C equals to 0. Cusp forms, let us just quickly recall. The F is called a cusp form. If at any cusps, if at any of these omega j's the Fourier expansion is supported on lambda n plus, namely only on positive definite matrices, right? So, and that should happen at all cusps, or equivalently at all elements of a group gamma n. So, next topic is the growth of the Fourier coefficients. It's a well-known fact that the Fourier coefficients of Siegel modular forms, which are anyway generalization of elliptic modular forms, there we have some, let's say, Delin's bound is known as Ramanujan conjecture, and in general we do know that they have some polynomial growth, and so let us recall that. Okay, so let f be an element of m n k gamma, which by which which is the notation for space of Siegel modular forms on gamma of weight k, and let its Fourier coefficients be a of t, a f of t maybe at the cusp infinity. Then one has the following estimate. It's usually called the Hecke bound, the Hecke estimate. A of f of t is bounded by some constant depending on the form by det t to the k, t positive definite, let's say. It's also true for other rank of t less than n. There is some other similar result. And for cusp forms, one can do a little better. The exponent is half of that. So this is called the Hecke bound, and so f of t is less than det t to the k by 2 for cusp form. And now this estimates also hold for other cusps. That's more or less obvious. One can see that. And so this is the question which I want to address in this talk. So this question is just the converse of the previous equation, or inequality, which I wrote. So if this 1 and 2, let's say 1, suppose af of t, let's say the exponent is k by 2, let's say. So if f of t is less than det t to the power k by 2 for some form, let's say on m n k gamma, not necessarily, of course, not necessarily a cusp form, then can you conclude from that whether it is a cusp form already? So that's the sort of converse of that inequality. So we make an even more general hypothesis in this regard, and that I call it just something k and gamma, depending on the parameters. There are 3 parameters here, so I'm just calling it k and gamma. So let gamma be a congruent subgroup, and let f be an element in m and k gamma, such that its Fourier coefficients supported on lambda n plus. So we are only considering at the positive definite matrices, that thing, satisfy the Hecke bound 2 with exponent k by 2, let's say, in at least one of the cusps. So there are finitely many cusps, choose any one of them, and suppose there is some growth condition given it at that cusp. Then it should be sufficient to conclude that f is a cusp form from that. And right, so in the rest of the talk we will try to state some results in support of the above hypothesis. And so this is the question and this is the hypothesis. Some known results I would like to recall now. Something. So this actually this must have been known much before, but this was started by Siegfried Bocherer in one of his papers. We got to know about it. So what he proved is the following. So he proved that for elliptic modular forms of weight 2 on gamma 0 n at the cusp infinity, let's say, he proved this thing, that the Hecke bound is enough to characterize cusp forms. And for this he used explicit description of the space of Eisenstein series for gamma 0 n, and just separated the Eisenstein part, and had to do some calculations to eliminate the Eisenstein part. So what remained was the cuspidal part, and I think small did it for higher weights. So Cohen and Martin proved the I think I wrote it wrongly. SP2 it should. So Cohen and Martin proved the degree 2 Siegel modular form case in level 1.
First case, if the weight is 2, we have to suppose the Hecke bound is a bit less than the Hecke bound, so we have to assume they did or something like that.
It's less than the Hecke bound.
Okay, where 2 is marked in this case.
Yeah. Little less than that. You have to assume.
Weight is 2, yes.
Okay. In our results will anyway will be with respect to general alpha. So yeah. So yeah, we will state our results later on in this talk in terms of general alpha. I don't know whether it covers that. I don't know. I have not checked. So so Conan and Martin proved the degree 2 Siegel modular forms case in the case of level 1, and by reducing this question to what are called Jacobi forms, which are some objects which are sitting in between Siegel modular forms and elliptic modular forms. They form a sort of bridge between them. So he reduced it one dimension of difficulty less, maybe I could say, and then argued like before, looked at the structure of the Eisenstein series there for Jacobi forms, and then the result followed. So Benjamin Linowitz proved an analog of the questions for Hilbert modular forms, again by the same method. And this is a very interesting paper. Mizuno proved the same thing, reproved the result of Conan and Martin using Imai's converse theorem, which is an analog of the Wales converse theorem for elliptic modular forms, characterizing Dirichlet series which come from modular forms. And now we have to apply it for Koeshar mass series, which is some Dirichlet series constructed out of the Fourier coefficients of a Siegel modular form. So he used that. It was a very nice result, and so it's a completely different proof. So I just want to say, and I think recently Chouye and Conan had proved a half integral weight analog of this question, and so let us indicate some difficulties which one might or does encounter as the degree becomes larger. And first, so as I said, the proof of Mizuno is different from all the others. All the others are more or less they just analyze the space of Eisenstein series by brute force. Sometimes we have to rule out some you have to prove some lower bounds on Fourier coefficients or some linear combinations of Fourier coefficients. Yeah.
We use those estimate only on fundamental discriminants. On fundamental indices. Not all here.
Okay. So let's focus on the Hecke bound only, alpha equal to k by 2. And so your space of modular forms is space of Eisenstein series with cusp forms. And if you assume that it's the Hecke bound, then we already know that the cusp forms do satisfy the Hecke bound, so we are left with Eisenstein series, linear combinations of Eisenstein series. So as was noted by Conan and Martin and other people also, a proof using the explicit structure of the Eisenstein series as the degree becomes large, and let's say on its congruent subgroups, then the situation is even more complicated. That seems to be difficult, simply because the growth properties of this Fourier coefficients are more or less similar. So there could be cancellations in the linear combinations of the Fourier coefficients which might reduce their size. There seems to be no direct way of ruling this in general. So same difficulty will arise if you want to use the Fourier Jacobi expansion and try to go to the Jacobi group. The same difficulty arises. So and as far as I know, there is no analog of Imai's converse theorem for higher degrees. As far as I know, there is one by Sugano or something, but Weishauer. Okay, but may not be usable as far as I know. As far as I know from Mizuno, it may not be very suitable for dealing with this. Maybe degree 2 was okay. So in this regard, we proved the following result. So suppose that you have a modular form on gamma 0 n, and suppose that you have some bound on the Fourier coefficients for positive definite t, and suppose that k is larger than this, little larger as comparison to n, 3 by 2n, and it's bigger than alpha plus n when n is 1, and it's bigger than 2n plus 1, and bigger than alpha plus n, and assume that n is square free, then you can conclude that f is a cusp form. So this was in 2012, And if you put here alpha equals to k by 2, namely the Hecke bound, and namely for n equals to 1 or n square free, you can conclude that f is a cusp form provided your k is a bit large. K is greater than 2n plus 1. If you just plug in. Now, there is a remark. So, so it will be interesting to find a proof for smaller weights, namely for k a bit bigger than n by 2 and 2n, because our proof won't apply here. So, we really need the weight to be large. So, and let's have a little idea of the proof. I think there is only one theorem. So first step is to reduce to eigenforms. So one can do this by diagonalizing the Hecke module generated by your starting function, and then you use Andrianov's identity, which you will recall, to get good convergence properties of the standard zeta function attached to f. And so what is the standard zeta function? So it is like this. It has an Euler product that converges in some half plane, and the Euler product is given like this. It's these are local factors, and alpha IPs are the Satake parameters attached to f. So we have some kind of an L function, and the Andrianov identity is the following. So you fix an element in lambda n plus with a of t naught non-zero. This can be done because your weight is a bit large, so you can always ensure such a t naught exists. And then the Andrianov identity will say that if you sum over the Fourier coefficients and make out a Dirichlet series like this, it will give you essentially the standard L functions, but up to some factors. That LS, even though it doesn't affect our calculations, it's a bunch of L functions, product of L functions there. Okay. And the next step would be so that's okay. So on the left hand side you do have some bound, right? We assume some bound on the Fourier coefficient AF of t. So on the left hand side you do have a bound, and from that you can conclude that this Dirichlet series on the left hand side converges in some half plane, right? And it's a holomorphic function. And so the next step would be to use the so-called Zarkovskaya relation, which just relates the standard L functions, standard zeta functions of degree n and degree n minus 1 like this for a non-cusp form. So phi f is non-zero, and let's not worry much about this. This phi is a standard Siegel operator, and this is the relation which is called the Zarkovskaya relation. And so what we find is that the left hand side of 3 and is holomorphic in this half plane, and that's because of your very good assumptions on the Fourier coefficients there on the Dirichlet series. Whereas this zeta function will give you a pole, right? Essentially, this is the argument, but one has to argue a little bit more too. But essentially, this is what you get, and so that will give you a contradiction, something, unless k is large. So what we have done is the following: the growth properties of the Fourier coefficients endow unusually good convergence property of some L function, and which is not possible unless f is cuspidal. So that's the idea. So in the case of gamma 0n, there could be some problems in applying the previous argument, namely phi of f could be 0, right? Phi of f could be non-zero at some other cusp, but phi of f could phi of f could be 0. There is no way to rule that out. So in that case, you might apply what is called the solution of the basis problem, which guarantees that every modular form will be a linear combination of theta series, right? This is due to Bocherer, Katsura, and Suzepilo, and for that you need the weight to be large. So you can plug in that, and then you can come around this difficulty of phi of f to non-vanishing or something. So that's but the main theme was comparing the Dirichlet-Andreev identity and the Zarkovskaya relation. And there is another thing that I want to say is that really the Hecke bound is not necessary. At first we thought Hecke bound is very special, but actually any alpha less than k minus n in the previous theorem it was stated in terms of a general alpha. Alpha is does not necessarily has to be k by 2. That's what I want to say. So any alpha less than k minus 1 will do, right? Provided k is a bit large. Right. So now I want to talk about some related results, namely degenerate indices. So a cusp form of degree n will have its degenerate Fourier coefficients 0. Right? By degenerate coefficients, I mean AF of t, the Fourier coefficients AF of t, but rank of t is less than n. Right? So that's by definition. Right? So therefore, I can ask the question, conversely, is it possible to characterize cuspidality by information only on the degenerate coefficients? So can you say that? And so there was a theorem, again joined with Bocherer in 2012. So if you assume some bound like this on the degenerate Fourier coefficients, and again if your k is a bit large, then you can conclude that f is a cusp form. So the degenerate coefficients are actually 0. Right? So and it didn't define the delta t. Delta t is almost like the determinant. Determinant is of course 0, so it's almost like the determinant. So this is one result. And one can also ask this question now several variants, right? You can ask this question for the Fourier-Jacobi coefficients. So I think we have also seen this in Professor Conant's talk, this Fourier-Jacobi expansion. So you can Fourier-Jacobi expand your modular form in several ways, corresponding to this decomposition. You decompose your Z in terms of block matrices, and then you collect together terms, and you get this Fourier-Jacobi expansion. And this phi q f of m are the Jacobi forms. I think this was already introduced. So now this index m is not an integer, it will be a matrix. Right? This q is the order of this tau prime. So it's really a matrix. And one obvious, more or less obvious statement is that if you assume that all these Fourier-Jacobi coefficients for positive definite indices are cuspidal, then you can conclude that your f was cuspidal. That more or less follows, because the Fourier coefficients of these Jacobi forms are nothing but the Fourier coefficients of your f, and you can then conclude that your f satisfies the Hecke bound, and you use our previous theorem. That's true. Yes, not on the coefficients. Sorry?
The norm.
Yeah.
Is a Hecke bound for phi q fm.
There is a bound, yes.
Yeah, but you take the norm of that.
Yes, yes, yeah. And also note that this phi fm are GLQ invariant, almost invariant. So if one is cuspidal, the other one is cuspidal. So we should really look at things modulo GLQ. Right? So there's another question. So if you know the cuspidality of phi q fm only on smaller subsets, let's say, not for all m, let's say only on some subset, will it be sufficient to conclude that f is cuspidal? So that's one question one can ask, and that's another result we have. So in this result says that when k is a bit large, and if you remove finitely many equivalence classes out of your indexing set, and you assume that the rest of whatever remains is cuspidal, then really your form will be cuspidal. That's all it says. It says that you can remove finitely many classes and still ensure cuspidality. That's all it says. and yeah, so K is a bit large again, not too much. And this condition actually comes from the theory of singular modular forms, but I don't want to talk about it. So there is a general question. What are the proper subsets of your indexing set, let's say lambda n plus, go by the modulo, the unimodular group, such that some suitable bound on the Fourier coefficients would give you cuspidality? How small, in some sense, I don't know, but how small your set has to be? So that's one question. Now let us get back to our hypothesis from the previous slides, K and gamma, which asked for the growth condition at only one cusp. So I forgot to mention, I mean, it was more or less clear that all these assertions were at the cusp infinity. Namely, you consider the usual Fourier expansion, right? And now we want to look at growth condition at an arbitrary cusp. So this makes life a bit difficult. So how much time do we have? 10 minutes. Okay. So in this regard, let me state the following theorem. Suppose, which is a very recent work with Siegfried Bocherer. So let gamma be an arbitrary congruous subgroup of SPN, okay, completely arbitrary, and look at the Fourier expansion of your form f at an arbitrary cusp, omega, let's say, and it will have some Fourier expansion like this and of this form, and suppose you have some bound on the Fourier coefficients with for some real alpha and t positive definite, and then you can conclude that f is a cusp form is if again k is a bit large and alpha is less than k minus n. So again, if you plug in your Hecke bound, then you get your hypothesis whatever k n gamma for any n gamma if again the weight is large. Again, we cannot dispense with this condition. This really comes from the proof. So yeah, so that's one. We really tried to improve this to go down, but it didn't work. So this is something I wanted to say, and so this proof is quite different from our previous approaches. So the proof is by a so-called local method, by which I mean, as opposed to the global ones in the previous approaches, we in the previous results we used some Andrianov identity, right? It's a global result, and instead of that, what we do here, we choose a very convenient Hecke subalgebra generated by some particular set of primes, namely p congruent to 1 mod the level or something, and you only use that subalgebra, and we again diagonalize, and we use the local versions of this Andrianov and this whatever Zarkovskaya, and surprisingly what happens when we do this, we see that we can argue algebraically. We do not need any L function. Okay, so this allows us to really argue algebraically. So what we do is we so corresponding to this Hecke algebra, we look at the growth of the eigenvalues corresponding to that primes, and we can really determine the asymptotic behavior of these eigenvalues under that particular Hecke subalgebra. And so there was no L functions involved, and so now I also want to talk about smaller weights. So I already mentioned a few times that we really wanted to do it also for smaller weights, and in this case we could only do it for the special congruence subgroups gamma 0 n, and for this what we used is the so-called Witt operator on modular forms. So what you do is put the off diagonal terms, you decompose your matrix on the upper half plane. Let's say it's on Hn. You can take tau to be on the upper half plane, and tau prime should be on Hn minus 1, and you can put those other off diagonal things to be 0. And it's known that Wf of tau and tau prime are modular forms in each variable. right? It's a modular form on tau, and also it's a modular form in terms of tau prime. So you can use this operator to prove this theorem. Suppose that again your f is in something m n k gamma 0 n, and it satisfies some bound at some cusp, that's the main point, at some arbitrary cusp, and let n be square free. So I will make a comment on this assumption, why we need n to be square free. And then you can conclude again that f is a cusp form if again alpha is less than k minus n plus 1 by 2. This is a very natural condition, because this is precisely the rate of growth of coefficients of Eisenstein series, k minus n plus 1 by 2. It's quite natural condition, and k is greater than 4, that's okay. And if we again plug in the Hecke bound, you really do get a bit smaller weight, right? So you get f is a cusp form if k is like n, and when n is square free, yeah. So the reason we really have to assume n is square free is because we have to write down explicit representatives of the cusps in terms of to be compatible with this decomposition, and that is only known for, that works only when n is square free. When n is not square free, it's a bit difficult. So that was the reason why n is assumed to be square free. It was only technical reason. Otherwise, yeah. So this is again a very recent work with Siegfried Bocherer. Yeah. I think with that I will stop.